let's get started. My name is Feng. I'm from Intel OTC, and currently I'm working in the virtualization technology team, focusing on the Intel hardware enabling for the new hardware features. And today my topic is shared virtual memory engine. Here we go. Sorry. Here is the agenda today. And first of all, I will give the motivation of SVM first. Then I will talk about what we have today and what we will get after having SVM. After that, there are some detailed information about SVM in hardware. Okay. Then I will describe why do we need SVM engine and what did we do in then for supporting SVM. And in the end, there is a summary about this topic. Okay, this is the motivation. First of all, OpenCL 2.0 is the biggest motivation of SVM. Since OpenCL 2.0 supports sharing virtual memory between CPU and the GPU, so to better support this feature, we need to add SVM support in hardware. And then, besides that, with SVM, we can reduce the communication latency between the CPU and the GPU, since the virtual address space is shared between CPU and the GPU. So the data sharing and their copy is possible. And also, with SVM, we can simplify the GPU programming. With SVM, we can share the page table between the CPU and the GPU. So we will have far fewer interfaces to use when doing the GPU programming. And sometimes we can simply reuse the shared pointer between them. Okay. This slide shows what we have today. From this slide, you can see the CPU and the GPU had independent virtual address space, and the CPU used the MMU to manage this virtual address space, and while the GPU used the GTT, which stands for the graphics translation table, to manage its virtual address space. Since these two virtual address spaces are totally independent, so there must be some overhead when doing the GPU programming, such as the data copy or data relocation operations may be needed. This is what we have after having SVM. Here you can see, after introducing SVM, the CPU and the GPU have a unified virtual address space, okay? And the GPU still use the MMU to manage it, while the CPU uses another page table, so-called first-level page table, to manage this virtual address space. And this first-level page table is newly introduced in the VTD hardware. And I will describe this first-level page table in details in the following slides. From here, you can see, since the virtual address space is shared between CPU and the GPU, so the GPU can use the same virtual address to execute the commands. So their copy is possible. Okay, this slide shows some detailed information about SVM in hardware. First of all, I want to describe some important concepts which are very important for people to better understand SVM. The first one is SVM. It stands for Shared Virtual Memory. And Pass ID. Pass ID is the abbreviation of Process Address Space ID, and it is a new extension to PCIe spec. In fact, Pass ID identifies the target virtual address space. And that means Pass ID is associated with a unique application's virtual address space. Okay. And after having SVM, we have two types of DMA requests. The First one is the DMA request without pass ID. In fact, this is what we have now. This is the legacy DMA request existing today, and the DMA request use the physical address. And there are another DMA request. It's a DMA request with pass ID. This is the DMA request using the application's virtual address. Okay, and the virtual address space is associated with the pass ID. Here are some extensions to VTD hardware to support this SVM. First, the root table, the root entry is extended, and the upper 64 bit is in use right now, and there are 2 pointers. The lower context table pointer and the upper context table pointer here, you can see here, which points to the extended context table, and also the context entry is extended, and it is extended to 256 bits. It also has 2 pointers. The first one is the pass ID table pointer. Here, it points to the pass ID table here. And the second one is the second level page table pointer. Okay, here. It points to the second level page table. In fact, the second level page table is exactly the current VTD page table. Okay, pass ID table is also newly introduced here. Each entry in the pass ID table points to the first level page table, which is associated with the unique pass ID. Okay, this slide shows some detailed information about the first level translation in the extended context. First of all, the first level translation table is used for translating the request with pass ID. That means it is used for translate those DMA requests with the application virtual address. From this figure, you can see when such a DMA request with pass ID is issued, we go through the extended root table, then the extended context table. Then we will find an entry in the pass ID. Then we will find the associated first level page table here, and we will do the address translation in this first level page table. And after that, we will get the physical address. This slide shows the second level translation in the extended way. In fact, there are 2 scenarios for this second level translation. This slide shows the first scenario. It is used for translating the request without pass ID. So this is how the VTD hardware works today. This kind of DMA request is without pass ID, and it uses the physical address. So here you can see, if this kind of DMA request is issued, we will go through the extended root table, then the extended context table, and we will directly do the address translation in the second level page table, and then we will get a physical address. And this slide shows the second scenario for the second level page translation. It is used for the translation requests with pass ID in the latitude mode. After introducing SVM, where we can configure the latitude mode in the extended context entry. Okay, here. We can set latitude mode in the extended context entry. Then, if that is the case, a DMA request with pass ID will go through the first level page table, then do the address translation in the second level page table. And after the first level table translation, we will get an IPA, which stands for intermediate physical address. And then we will do the address translation for this IPA in the second level page table, and then we will get the HPA. Okay, here. This is another new feature introduced together with the SVM. It's called recoverable address translation fault. So with this, where we have the page fault capability on the device side. First of all, if a device wants to support this capability, it must have two PCIe capabilities. The first one is the PRS, which stands for the page request service, and the next one is ATS, stands for the address translation request service. Okay, here is the flow of the recoverable address translation fault handling. In the beginning, the device will send out the translation request to the VTD engine. Okay, here you can see to request the VTD hardware to do the address translation for the device. If the VTD hardware can do the address translation, okay, in its page table, then it will send back the translated address to the device. And after that, the device can use this translated address to issue a DMA request with it. So it will do everything works fine. But if the VTD hardware cannot do the address translation for these translation requests, okay, it will send back a response to the device. Then a recoverable fault. Sorry. Then a recoverable fault will be discovered in the device side here. And after that, the device will send the page request to the VTD hardware, and the VTD hardware will include this page request in the page request buffer in hardware. And then sometime later, it will notify the CPU via interrupt to let the CPU do the real page allocation for the devices here. So in the CPU side, it will do the real allocation. After it is done, it will send back the page response here to the VTD engine from the invalidation queue. So the VTD engine will get this response from the invalidation queue and then send the response to the device. So after this whole process is successful, the device can replay the original translation request. And this time, it should get the translated address because the page is allocated by the CPU, and the mapping should be in the page table. And the VTD hardware can do the address translation for this translation request. So the device will get the translated address and send the DMA request with this translated address again. Okay. So talking so many about SVM itself. So why do we need SVM then? Well, you know, the new Intel graphic devices support SVM, and so it can work in the SVM mode. So to make this kind of devices work correctly in the guest as assigned devices, okay, we need to do some enabling work in them, and there are some more detailed slides in the following pages. Basically, this is the SVM architecture in Zen from the implementation point of view. Here, I just want to I'd like just to give a brief high-level introduction here because there are more detailed information about each part in the following slides. And from the left side, you can see we need to expose virtual VTD with the SVM extension to the guest, so that the guest can issue the DMA request with pass ID. That means it can use the application, the virtual address, to send the DMA request. Here, you can see. And in the middle part, we need to shadow the guest extended root table and the extended context table here, shadow. You can see. Then, if the guest issue the DMA request with pass ID, we can do the address translation in the nested way. Here, the first level page table, then the second level page table. And here in the right side, we need to handle the address translation for the guests. Okay. Okay, let's go to the details. Okay, this one is the virtual ATD. In fact, virtual ATD is not something new. There are some implementations in the QEMU or maybe in Zim itself. But here, I just want to highlight some key capabilities we need to expose to guests for this virtual ATD to support the SVM. The first one is the cache mode. We need to expose cache mode as 1 to the guest. This is very important for us because the spec says that any software updates to any remapping structures need to do explicit invalidation of the caches if the CM is 1. Okay, so that includes the updates to the long present entries and the updates to the present entries resulting in transition fault. Okay, so this rule is very important for us to shadow the extended root table and the extended context table. And there are some detailed description about this shadow things in the next page. And of course, the pass ID table, or the pass ID, we need to expose this capability to the guest. Because with this pass ID capability, the guest can issue the DMA request with pass ID. That means you can use the guest's application virtual address to send the DMA. There are 2 other capabilities. The first one is the PRS, stands for Page Request Service, and another one is queue invalidation. These 2 capabilities are important. We need to use them to handle the recoverable address translation for the guests. Okay, these slides show the the VTD page table virtualization. Basically, it includes the shadow things I mentioned before. As I mentioned before, we need to expose the CM as 1 to the guest. So each time the guest updates to the extended root entry or updates to the extended context entry, it leads to do explicit invalidation of the caches. So in the hypervisor side, we can intercept and pass this kind of invalidation operations. Then that means we can get the value each time the guest updates to the extended root entry and the extended context entry here. So it's easy for us to shadow it in the host side. Okay, and this is how we shadow. So which items in the guest's extended root table and the extended context table leads to be shadowed? Where? For most of the field in the root entry and the context entry, we just directly copy them and copy them from the guest and put it in the shadow table, because they work for us. They just work for us. But there are some special field, such as the first one is second level page table. Here, first level page table pointer, we need to point to the host side GPA to HPA page table. In fact, it's the second level translation table. We need to point it to here. And another one is the last enabling bit. This bit is in the extended context entry. We need to set this bit so we can do the address translation in the last way for the DMA request with pass ID. Here you can see from the right figure. If a DMA request with pass ID is issued here, we will go through the shadow root entry first, then the shadow context entry here, and we will find the guest side page table here. This is the guest side page table because we have a first level page table pointer. We just copy it from the guest. Okay, so we will point to the guest side page pass ID table. Then we will find an entry in it. And then we will do the address translation in the associated first level page table here. We will get the GPA. And then we will do the address translation for this GPA in this second level translation table here. After that, we will get the HPA. Okay. Okay, this slide shows the non-recoverable fault handling. As you may know, for non-recoverable fault handling, the VMM and the OS usually don't have a very good way to handle it. Sometimes they just reset the device. So here comes two possible solutions. The first one is that we don't emulate the non-recoverable fault handling logic in the hypervisor. Which, if the non-recoverable fault happens for the guests, we just reset the device in the host side and detach the guests from detach the devices from the guests, and maybe reattach it to the guests. And then another solution is that we can do a full emulation of the non-recoverable fault handling logic according to the VTD spec. So if this way we need to do a lot of emulation, and we need to notify the guest via the virtual MSI if the non-recoverable fault happened for the guests. Okay, this slide shows the recoverable fault handling. In fact, we need to do something for the guest to support this recoverable fault handling here. As I mentioned before, if a device needs to support this recoverable fault handling, it should have two capabilities: PRS and ATS. Okay, first of all, here the device will send the translation request to the VTD hardware, and the VTD will, if the VTD cannot do the address translation for this translation request, it will send back a response to the device here. And then on the device side, it will find the recoverable fault. Then the device will send the page request to the VTD hardware, and the hardware will include this page request in the local PRQ, stands for page request queue. Then on the software side, we will check this page request, and whether it is without or with pass ID. If it is without pass ID, that means this page request is for the host, so we can totally handle it inside the host. Here, if it is without pass ID, we will handle it in the host side recoverable fault handler. And if it is with pass ID, that means it's for the guest. Here, we will put this. We will get the page request from the PRQ and put the page request in the virtual PRQ. Here, the virtual PRQ for the guest. This is inside the virtual VTD. Virtual PRQ for the guest, and notify the guest via the virtual MSI here. And when after the guest receives this interrupt, it will do the page allocation for the device in its local guest recoverable fault handler. And after it is done, it will send back the response to the virtual invalidation queue for the guests. And we will get the response from the virtual invalidation queue and put it in the real hardware invalidation queue here. Then the VTD hardware will get the response from the this invalidation queue and send the response to the device. And after it is done, the device can replay the original address translation, and it should get the translated address and continue to send out the DMA request with this translated address. Okay. Okay. Here is the summary. First of all, I want you guys to make it in mind that after SVM, we can share the page table between CPU and the GPU. And there are two types of DMA requests. One is with pass ID, and one is without pass ID. So the there are another newly introduced page table, so-called first level page table in the VTD hardware to support this SVM. And from the software implementation of Vue, hypervisor implementation of Vue, where we need to expose the virtual VTD with the SVM extension to the guests, and we need to shadow the extended root table and the extended contact table. And we also need to handle the non-recoverable and the recoverable transition forward for the guests. Okay, that's all. Thank you. Okay. So any questions?
What hardware did you say will have it? Bravo?
No, maybe the next generation scanning maybe don't have full supply, doesn't have the full supply support for this feature. The next generation after scanning should have the full support for this feature. Right, Don?
How set on the name are you? We've already got one thing called SVM. You're suggesting a second thing called SVM, and Colo are introducing a third thing called SVM. We have quite a lot of SVM in the code at the moment.
Yeah.
Unfortunately, we have minimal control of that.
Fair enough.
So the other thing is, you mentioned in Q you're going to need to support to expose a virtual IOM view.
Yeah.
Now, the architecture that it is QEMU exposed is a very ancient one. I think it's PIX4. So does that mean you also need to actually expose the Q45 chipset to make this all work with ATS support? That's our
I'm
heading.
not sure where we've gone. I mean, the fact that we're exposing the PII X4 is kind of an artifact. It's not a real thing. So if we were to add VTD support to that particular architecture, it wouldn't be the end of the world.
I mean,
It might be a little strange, but you know.
you've already got PCI Express devices out of the PIX4 chip these days.
So it's already not a real emulation of that hardware. So I don't know that we've actually come to a decision.
Okay.
So we did have a discussion about this in
Hackathon?
Shanghai.
Yeah.
Yan and I are fairly certain we don't need any QEMU input whatsoever.
Oh.
Zen already has an IOA PIC implementation in the hypervisor from when AMD did passive support. It's a little bit broken at the moment. Nothing ever turns it on. But there is already an implementation in hypervisor, and even with
But how would you be able to expose the VTD registers to
well,
the changing QEMU?
why does it need to be QEMU? It's Zen that controls all of this. You don't need 2 round trip times the QEMU.
You're saying the VTD information.
So
It would have to be done there anyway. And already with the DMAR table, you can specify one IOMU on one device and separate IOMU on everything else. So at that point, you have
If you talk to
yeah,
That's acceptable.
it completely removes QEMU from the equation. You'd already need this emulation in the hypervisor anyway, because of the way in which it's set up. And there's already what appears to be most of one already in the hypervisor.
Well, we recognize that exposing VTD is kind of a bit of a machine, and that's why this is a feature. So we're very
Yeah.
So I already run out of time. So if you have any further questions, just come to me. Okay. Thank you. Okay. Thank you.